All right, let's get started. So the the lecture video for last lecture is up, and I put the notes up immediately as soon as it was sent to me. I might go back and do a little editing. Now, those are all up. Let me know if you can't view the video. Just a reminder of some of the things from last time, plus maybe one bullet that I didn't mention last time, but I should have. And we're going to eventually get back to using that again. So today we're going to continue with streaming algorithms. I'm going to focus on a different couple of streaming problems. Most of the time will be spent on something called the distinct elements problem. Okay. So last time we did like approximate counting. That was Morris's algorithm, right? And Morris's algorithm gave us an unbiased estimator, and then to get a good approximation with high probability, well, first we took the average of many estimators, which I just called Morris plus, and then we took the median of a bunch of those, and I called that Morris plus plus. Okay, this is non-standard terminology. I just made that up. But this idea of developing an unbiased estimator, like a randomized, basically setting up an algorithm that outputs a random variable, which is an unbiased estimator of what you want, then taking the average of many such estimators and then taking the median of a bunch of those is something that is very common in the design of streaming algorithms. Okay, so this idea of plussing is something you should feel comfortable with, and we're going to do another example today. Okay, and this is probably the last example where I'm going to really go through all the details painfully, and then from then on I'll assume that you're comfortable with the plussing and plussing. Okay, so today we're going to look at another streaming problem, which is called the distinct elements problem. And if we get time, we're also going to look at norm estimation. If we don't have time to do this fully, I'll put it in the notes. Okay, good. So what is the distinct elements problem? In the literature, you often hear this problem called the F0 problem for a reason that'll become clearer, I guess, at the end of lecture. Okay. So you see a stream of integers. I use this shorthand to denote the set 1 up to n. Okay. So each stream update is a number between 1 and n, and the output is the number of distinct integers seen. And as last time, the goal is going to be to minimize space consumption. Okay. So what are two straightforward algorithms for solving this problem? And how much space do they use? So someone give me one straightforward algorithm. Let's say you know M and N. Yeah. Yeah, basically keep a bit array of size n, and then flip the ith bit to 1 if you ever see an integer I in the stream. Okay, so straightforward algorithms. So the first one is a bit array of length n. Okay. Okay, what's another straightforward algorithm? So what is this? This uses space, which is n bits, right? Okay. What's another algorithm? Something that gets you a bound that's not n bits, some other bound, which is incomparable. What might you do if m is very small, if the length of the stream is very small? Any takers? Yeah. Yeah, just keep a list of all the numbers you've ever seen. There are m of them. Each number is between 1 and n, so it takes log n bits to store a number. So just store the whole stream. And that's something like m times log n bits of space, whereas this is n bits. So we can get the min of n and m log n bits. Okay? And okay, we're going to see after the algorithm, we're going to talk about lower bounds, but you can't really beat this bound, okay, if you want to solve this problem exactly. But just like last time with Morris's algorithm, we're going to be okay with getting a randomized algorithm which outputs an approximate solution with high probability. Okay? So again, randomness and approximation will settle for outputting, let's call it t tilde, such that probability that t minus t tilde is bigger than epsilon t is at most delta, where t here is the true answer. Okay? Okay, good. So, and the first algorithm that got us something like this is due to Flageolet and Martin. This was back in 83. Okay. Okay, great. So first I'm going to show you an idealized algorithm, which is going to give us a good space complexity. And then I'm going to transform it from an idealized algorithm to one that you can actually implement on a computer. Okay? So this was the heart of the idea from Flageolet and Martin. Okay, so the algorithm. So the first thing we're going to do is we're going to pick a random h mapping the input universe into the continuous interval from 0 to 1. Okay, so already, so I should have put this is idealized. Idealized algorithm. So already there's something wrong with this algorithm, right? I mean, what's wrong with step 1? There are two things wrong with step 1. Yeah. Right, so yeah, so I guess that sums up both problems. So the first issue is to store a random function, you're going to need at least n space. You're storing n random numbers. And the second thing is these are real numbers, right? And my computer only has finite precision. Okay, so we're going to take care of both of those soon. Okay, so second step is we're going to maintain only one number in memory. Which is the minimum hash value we've ever seen. Okay? And then what we're going to do at the end is output 1 over x minus 1. Okay? Now, some intuition for where this algorithm is coming from. So this random function it's a consistent function, right? If we see 5 in the stream and compute h of 5, then later in the stream, if we see 5 again, h of 5 will be the same number, right? So what are we actually maintaining in this variable x? So x is a random variable, and it's the minimum of t independent uniform 0, 1 random variables, right? For each of the t people in the stream, they're giving you a random number, h of I, and you're maintaining the minimum of all those h of i's. That's t independent random numbers, right? So here's 0. Here's 1. Suppose t was 1. We just had one random number between 0 and 1. What do you expect one random number between 0 and 1 to be? Right? A half. What if you had two random numbers between 0 and 1? The picture you expect is, kind of evenly spaced, which is a third and 2/3. If you had t random numbers, you expect them evenly spaced, which means 1 over t plus 1, 2 over t plus 1, et cetera. Right? So the expectation of x is 1 over t plus 1. So 1 over x is t plus 1, minus 1 is t. Okay, so great. I apologize. I think if anyone was in 224 a year ago, I might have done this example as well, but we're going to soon get into stuff that you've never seen. At least I don't think so. OK, great. So let's prove this claim right here. Claim the expectation of x is, let me write it here. The expectation of x is equal to 1 over t plus 1. Okay, the proof. The expectation of x is the integral from 0 to infinity of the probability that x is bigger than lambda d lambda. Okay. And that's equal to the probability that the integral from 0 to infinity of the probability that for all I in the stream, h of I is probably that x is bigger than lambda. Yeah, so the minimum value has to be bigger than lambda, right? Which means that for all I in the stream, h of I is bigger than lambda. D-lambda. Okay. But these h of i's are independent. H is a totally random function. So this is equal to the integral of the product over I from 1 to t, or let me call it r from 1 to t, of probability that h of I, r, is bigger than lambda d lambda. But what's the probability that the hash value is bigger than lambda? Well, if lambda is bigger than 1, then it's 0. H of I is never bigger than 1. If lambda is between 0 and 1, then it's 1 minus lambda. Right? The probability that you're bigger than lambda is 1 minus lambda. So this thing here is equal to the integral from 0 to 1 of 1 minus lambda to the t d lambda. And then you do a variable substitution. This is equal to the integral from 0 to 1 u to the t du. And that's equal to 1 over t plus 1. Okay. So I'm doing things slightly differently than last time, but it's OK. I mean, last time I took the entire estimator and I computed its expectation, and then I took the entire estimator and computed its variance. Okay. This time I'm just focusing on x. Okay, and then I'm saying, what's the expectation of x? Okay, and what's the variance of x? And then what I'm going to do is I'm going to replace this x with an average of many of them. Okay, so we'll get there in a second. But I want to know the variance of x, right? So remember, the variance of x is the first bullet, because I want to apply Chebyshev. And the variance of x requires me to understand the expectation of x squared. Okay, so claim, and I won't do this one, I won't do every single calculation, but the claim is that expectation of x squared is equal to 2 over t plus 1, t plus 2. Okay, and the proof is very similar. Proof, the expectation of x squared is equal to the integral from 0 to 1 of the probability that x squared is bigger than lambda d lambda. Okay. And that's the same thing as saying that x is bigger than root lambda. So just running through the same kind of steps, you get that this is equal to the integral from 0 to 1 of 1 minus root lambda to the t d lambda. And then now what I'm going to do is I'm going to say u is equal to 1 minus root lambda, which implies that lambda is equal to 1 minus u squared, which implies that d lambda is minus 2 1 minus u du or something like that, I think. Yeah. So if you plug that in here, you'll get that this thing is equal to the integral from 0 to 1 2 times the integral from 0 to 1 of u to the t, I think u 1 minus u or u minus 1. And 1 minus u du. Right, this is u to the t minus u to the t plus 1. And then you'll get what I said. Okay? Which the variance is the difference of the two. So if you do that calculation, which I won't do here, the variance of x is equal to this minus the square of that, which gets you something like, I think, t over t plus 1 squared, t plus 2. Which is less than 1 over t plus 1 squared, right? Which is the same thing as the expectation of x squared. Okay? Okay, good. So now we're going to do the standard plussing, right? Which is averaging a bunch of these guys. So let me call this algorithm FM for Flageolet-Martin. So now FM plus is instantiate call it Q, which is 1 over epsilon squared eta FMs independently. Okay. And output the average of, well, okay, let's see. Let xi come from, xi is the counter that's stored by the ith instantiation of the algorithm. Okay, and now what I'm going to output is 1 over the average, 1 over q times the sum of xi's. I goes from 1 to q minus 1. Okay. And notice that now the variance of this thing, 1 over q, first of all, what's the expectation? Right, what's the expectation of this average? It's the same as what it used to be, 1 over t plus 1, right? Because linearity of expectation, if you sum a bunch of random variables, the expectation is sum. And then so this would give you q times the old expectation, but I divided by q. And the variance, okay, the variance, well, by the second bullet, when you sum up independent random variables, the variance is add. So the variance of this sum would be q times the old variance. But whenever you take a random variable and scale it by some factor c, the variance gets multiplied by c squared. Right? So you can verify, basically there's a square in that definition. Right? So if you replace x with cx, then you have the expectation of cx minus expectation cx squared. So the c gets squared. Right? So we get the old variance times q divided by q squared, which means we divided the variance by q. So we improved the variance. So this thing is equal to 1 over q times what the old variance used to be, which is less than the expectation of x squared over q. Just using what's over there. Okay, good. So now let's finish the analysis. So now what I want to say is that, let me call this number, let me call this z. Okay. The probability, so claim, the probability that z minus 1 over t plus 1 is greater than epsilon over t plus 1 is at most eta. What's eta? I instantiated q to be 1 over epsilon squared eta. Okay, and the proof is just Chebyshev. The probability that I get that deviation is at most the variance. Well, first of all, over lambda squared. So I get t plus 1 squared over epsilon squared. And then the variance is at most 1 over q, t plus 1 squared. That cancels that. And I rigged q so that this thing is less than eta, right? Or this thing is equal to eta. Okay. Questions? Yeah.
So I guess you alluded to this before, but we're not concerned that 1 over x is not going to be unbiased in expectation.
Oh, but I'm never.
I get that we're analyzing x right now.
Yeah.
And are we just okay because for large t, that means that 1 over x will be close to an expectation to t or t plus 1 or whatever it is? Or
Oh, I mean, so we're not making any such assumption, right? So regardless of what t is, The expectation of x is always 1 over t plus 1.
Right.
And by averaging many copies, what is this saying?
Oh, yeah.
Right?
No, I get that.
Yeah.
Your number 3 says output 1 over that thing minus 1.
Yeah.
But we're not, like you said, we're not analyzing the expectation of 1 over that thing. We're analyzing the expectation of.
Yeah, just the denominator. We're just saying that the denominator is super close to 1 over t plus 1.
And so then, like, the fact that we're non-linearly transforming it, we're just not going to worry about that.
Oh, we'll worry about it, but it'll be fine, right? So now claim. So just to make you at ease. So now the claim is the probability that 1 over q of that sum of xi's minus 1. The probability that our estimator deviates by t by more than epsilon t, I want to say is more than eta. Maybe I'll get some. Maybe I'll lose a constant factor in the epsilon.
I see. So it may not be right in expectations, but it's close with that probability.
Yeah, and that's all I care about anyway. Yeah, right. And the proof of that is just, let me call this claim 2, and let me call this claim 1. By claim 1, with probability 1 minus eta, we have, this is something that's within a 1 plus epsilon factor of the truth, right? The deviation is epsilon over t plus 1. So multiplicatively, it's within 1 plus epsilon of what we care about. We have that output is actually 1 over 1 plus or minus epsilon 1 over t plus 1 minus 1. Right? But 1 over 1 minus epsilon is basically 1 plus epsilon. 1 over 1 plus epsilon is basically 1 minus epsilon, up to changing epsilon by a constant. Okay, you can calculate that for yourself. So this is 1 plus or minus O of epsilon t plus 1 minus 1. Okay, and as long as t is not 0, well, if t is 0, that's very easy to check. Basically, there's no stream. Okay, so as long as t is not 0, this thing is equal to, well, what is this? This is 1 plus or minus O of epsilon t plus or minus O of epsilon. Right, but this is a much smaller error than epsilon t as long as t is not 0. So we're fine. Yeah, so yeah, this example was a little different from last lecture's example in that it's not the estimator itself whose expectation we're calculating and whose variance we're bounding, but there's some random variable somewhere in the estimator, and we're just saying that we can apply the plus 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 trick to that thing. Questions? Okay. So the space here, well, okay, again, there's this issue of the algorithm being idealized. H is taking n space already, okay? But if you ignore the fact that we have to store H, this algorithm is maintaining Q numbers, right? So for some definition of space, the space is 1 over epsilon squared eta. Okay. And if I want failure probability delta, one thing I could do is I could just set eta to be delta. But now my space is 1 over epsilon squared times 1 over delta, right? And we had a trick last time for improving the dependence on delta, which is I'm not going to try and get failure probability delta in one shot. I'm going to settle for eta being a constant, like a third, right? And then I'm going to take the median of many such estimators. So that's the plus plussing. Okay, so let's do that. And then this will be the last time I do this in such great detail, and then from now on you'll be you should have this sequence of steps at your fingertips. So then now finally we have fm plus plus. We're going to instantiate, so step 1, instantiate S, which is something like 24 times ln 2 over delta independent copies of Fm plus, with eta being a third. Output the median of 1 over zj minus 1, where j goes from 1 to s. So zj is the output of fmj. Okay. And what's the analysis for this? So the analysis, so claim, let me call this t hat. The claim is that the probability that t hat minus t is bigger than epsilon t is at most delta. And the proof of that is, so let's define some indicator random variables, yj. Let yj be 1 if 1 over zj minus 1 minus t is bigger than epsilon t, and 0 otherwise. Basically, yj is 1 if the jth fm plus j. So we have these s independent copies of fm plus. Yj is an indicator random variable telling us whether the jth copy screwed up and didn't give us a good estimate. Okay. Now, what do we know from claim 2? Right? Claim 2 says that for all j, the expectation of yj is at most a third. Right? The expectation of yj is the probability that the jth copy failed. That's at most a third. So for the median to be a bad estimate, right? For the median to be a bad estimate, it means that strictly more than half the copies failed. So median fails implies that the sum from j goes from 1 to s of yj is bigger than s over 2, right? But the expectation of this sum is s over 3. So it had to deviate by its expectation by quite a lot. So, right? So the probability that sum of yj is bigger than s over 2 is the same thing as the probability that the sum of yj minus s over 3 is bigger than s over 6. Right? So by the way, so for the purposes of bounding this, tail bound, here we have a bunch of, basically Bernoulli random variables, each with expectation at most a third. So the tail bound will only get worse if we replace them with Bernoulli random variables with parameter exactly a third. Right? Those only have a bigger probability of being bigger. So let's just pretend that these yj's actually were random variables which were 1 with probability a third and 0 with probability 2/3. So now what is this? This is equal to the probability that the sum of yj's minus the expectation of the sum of yj's is bigger than 1/2 times the expectation of their sum. And this is exactly the setup of Chernoff, right? I have independent random variables, my yj's, which are between 0 and 1. The probability that it deviates by its expectation by more than epsilon times the expectation, epsilon is now 1/2, is some exponential decay. Actually, you don't even need this 2 if you remove the absolute values. We don't have the absolute values, so we don't even need the 2. So I could have made this 2 a 1. So this thing is at most e to the minus, in fact, okay, it's okay. I could have even made that 3 in the denominator be a 2 in the case where I only care about the upper bound. Whatever, doesn't matter so much if you don't care about constants. So here I put e to the minus 1/2 squared times the expectation, which is s over 3, over 3, right? I'm just invoking Chernoff. And I picked s exactly so that this thing is less than delta. Right, this is 4 times 3 is 12, times 3 is 36. Well, okay, so 36. Okay, so this is the general plus-plus-plussing paradigm for the second time, and hopefully now you all are plus-plus-plussing experts. Any questions about any of this? Yeah.
So you take the median of the means.
The median of the mean, that's right.
Is there any particular reason? I get that the sequence of inequalities that works out, but why is the median of the means better than mean of the means?
Oh, why not just take the mean of a bunch of copies?
I never knew median or means worked better in any domain.
Oh, why take median of means as opposed to simply? So.
Mean to make the variance small, and then median works better when the variance is small.
So, okay, so one thing about, okay, so there are some, we're going to see later in the class, there are some cases where you can really just take the mean of, so here, our final space is big O of log 1 over delta over epsilon squared, right? So maybe I should write that down. Ignoring H. This is ignoring the space to store H. So you could say, why don't I just average this many copies? Okay. So depending on how your random variable behaves, sometimes that works. And the way that you would analyze it is kind of variance. Variance is just not strong enough to give you this kind of log 1 over delta kind of behavior. You would have to go to higher moments. So from the first lecture, I said, taking the square here, right? So up here, how did we prove Chebyshev? We just did Markov on the second power of both sides. So you could imagine taking the pth power of both sides. And if you take p really big, then depending on how the moments of your random variable behave, you can get this straight up from averaging sometimes. But if the moments of your random variable, if the high moments are too big, then that wouldn't work. Okay, so right. So yeah, sometimes it works, sometimes it doesn't. But this median of means thing works as long as you can get the variance bounded. Did I answer your question? Okay. Any other questions? Okay. So I want to do 2 more things with distinct elements. One is this is an idealized algorithm because we had to know this H. Okay. And then the second thing is I want to talk about why. So we have a randomized and approximate algorithm, right? What if I just wanted an approximate algorithm, which isn't randomized, like a deterministic algorithm, which always outputs a good approximation of the answer? I'm going to show you that that's impossible. Then you could ask the other question. What if I want a randomized algorithm that outputs the exact answer with high probability, but has some probability of outputting junk? And that's also impossible. By impossible, I mean getting space better than the trivial solutions of remembering everything. Okay. So I'm going to show you the deterministic proof in class, and the randomized will probably be on your first P set, which will come out probably tomorrow or Thursday. Good. And then in the remaining time, I will say something about another problem. right? So I don't want to have this assumption that I have this access to this perfectly random hash function h, which takes at least n space to store, right? So, so 124 is a prereq, so I will assume you've seen hashing, but I'm going to cover the definitions again, okay, just so we're all on the same page for sure. So definition. A family H of functions mapping A to B is k-wise independent if kind of for all j1, jk in B, and also for all distinct I1, ik in A, if you take a random function h from this family, a uniformly random function from this family, then the probability that h of I1 is equal to j1 and h of ik is equal to jk. Okay, what do you think I should put here? I want to say that basically the function behaves like a random function. If this were a random function, what would be the probability of this happening? What's the probability that h of I is equal to j? 1 over b. So if this is actually a totally random function, what's this probability? Yeah, 1 over b to the k. So that's the definition of k-wise independent. Okay? That it behaves the way that a random function would. So what's an example of a family of functions which is k-wise independent for any k? So, yeah, the set of all functions, right? The family of all functions is k-wise independent for any k. Because then picking a random function out of that family is the same thing as picking a totally random function. Okay, so if you pick h to be the set of all functions mapping A to B, this is k-wise independent for all k. Okay, so if you want to store a function little h from a family script h, how many bits do you need to store little h? Right, in general, if I have a set of elements and I want to represent an element from that set, how many bits do I need to represent an element from that set? Log the size of the set, right? So this script h has size, which is, I guess, something like b to the a, which implies h represented in a times log b bits. Right? So the name of the game really is, right, at the end of the day, we're going to instantiate some kind of version of this algorithm with some k-wise independent family. Okay? So if you have to take into consideration that the algorithm has to store h, what you really want is your family to be small, because then you can store h using few bits. So let me define another family. So let's let A equal B equal P, where is that what I want to do? P is a prime. Okay. And then I'm going to define H poly as being the family of the set of all degree at most k minus 1 polynomials with coefficients. Okay. Let's just say over F. Yeah. Okay, so I just mean the set of all polynomials of degree at most k minus 1, where the coefficients are between 0 and p minus 1. Okay. And how do you actually evaluate the hash function on an input? You evaluate the polynomial mod p. Okay. So now, what's the size of H poly? Yeah, it's, well, that's, I guess, log the size, but yeah. Right, so basically if you have a degree at most k minus 1 polynomial, that means there are k coefficients. Each one is a number between 0 and p minus 1, so there are p possibilities. So this is equal to p to the k, which implies H can be represented in k times log p bits. Right? A totally random function from p to the p would take p log p bits. But here we're getting it down to k log p bits. Right? So if you imagine we're setting k to be like 2 or something, then this is only log p bits. We can actually store H using very little memory. Okay? And in fact, you can even set this thing up where, Q actually is a prime power. And then you do it over this finite field. Okay? I don't want to, if you're thinking of P as if you're not so familiar with abstract algebra, it's okay. That's not going to be a component in this class, but okay. Think of P as a prime. So claim, I'm not going to prove this claim. I'll put the proof in the notes, is that H poly is k-wise independent. Essentially the reason, I'm not going to write the proof down, essentially the reason is by interpolation. Okay? So if you give me any set of j's and any distinct i's, k of them, there's always exactly one polynomial which will make all of those evaluations come out the way you want. Right? So there's exactly one polynomial over, and then you have to divide by, what's the probability that you pick that polynomial? Well, it's 1 over the total number of polynomials, but the total number of polynomials is p to the k, or q to the k. So the proof is by basically interpolation, or the fundamental theorem of algebra. Okay, I'll put that in the notes. So now let's do a version of Flageolet-Martin, which is not idealized. So first, what I'm going to tell you is how to get not a 1 plus epsilon approximation of the answer, but a constant factor approximation of the algorithm, of the output, of the number of distinct elements. And we're going to do it in log n space, log n bits. And by this I mean, what I mean by this, I mean t tilde is going to be at most ct and at least t over c for some constant c with good probability. It's going to be a randomized algorithm. So one, pick H from a 2-wise family mapping n to n. Assume n is a power of 2. So that construction there works as long as the input and the output are equal in a prime power. So let's just pretend that n is a power of 2. If n is not power of 2, what do you do? Yeah, you round up to the nearest power of 2. Yeah. Right, so I don't want to get into that because it requires too much algebra. But yeah, so what you could do, sorry? Yeah, you could also, yeah, so rounding up to the next prime also wouldn't quite work for what I'm about to say, although rounding up to a much larger prime would work for what I'm about to say. Okay, so I'll tell you what I'm about to say. But yeah, you can do arithmetic even over these other fields, but then, okay, I'll say something. If you don't know what I'm saying, that's okay, because you don't need to know abstract algebra. But basically, to work over an extension field, what you need is, let's say q to the k. Sorry, let's say q is p to the k, or not k, because I'm already talking about k. Q is p to the r, where p is prime. What you need is an irreducible polynomial of degree r over the base field, and then you do multiplication mod that polynomial, and then you basically add vectors mod p, add coefficients mod p. That's how you do arithmetic over an extension field. But forget about that if you don't care about it. But let's just pretend that there are other, by the way, so there's actually a wiki page on pairwise independent hash functions. So this is one example. There are other implementations of pairwise independent hash functions where you really only need to do like bit shifts and other bitwise operations. You don't even need to deal with like multiplication over a field. Okay, so check wiki page for pairwise hash functions, and you'll see some really fast implementations of them that just require like a shift, and maybe yeah, you need a multiply as well, but like shifts and multiplies and nothing fancy. But let's just pretend that we have this. Yeah, so if n is not a power of 2, just round up to the nearest power of 2. That will at most double n, and then log of 2n is basically log n anyway. Okay. I only care about things up to big O. Good, so what we're going to do is maintain x, which is the max over I in the stream of the least significant bit of h of I. LSB is least significant bit, the index of the least significant bit. And then what we're going to do is output 2 to the x. Okay. Questions about the algorithm? what the algorithm is. I haven't proven to you that it does anything useful, but that's the algorithm. Okay. And before I write anything down, let's talk about why this makes some sense. Just focus on our particular integer I in the stream. What's the probability that the least significant bit of I is j, is index j? Let's say we start counting from 0. The bit, if you write down h of I in binary, the bit all the way to the right is bit 0, and then bit 1, bit 2, bit 3, et cetera. Right, so what's the probability that the least significant bit of h of I is equal to j? Yeah, or 1 over 2 to the j plus 1. Yeah, so everyone to the right of it has to be 0, and then j himself has to be 1. So there are j plus 1 things that need to, j plus 1 bits that need to be exactly the way you want them. Right? So the probability that a particular person in the stream has LSBJ is 1 over 2 to the j plus 1, but let's say roughly 1 over 2 to the j. So the expected number of people in the stream who have least significant bit j is t over 2 to the j. Right? Or what's the probability that they're least what's the expected number of people who have least significant bit at least j? It's t over 2 to the j plus t over 2 to the j plus 1 plus some geometric series. It's still roughly t over 2 to the j. Right? So that means that when j is about log t, you expect about 1 person there. Right? You expect to have some people there. But when j is much bigger than log t, you expect very few. You expect like much less than 1. So with good probability, you're not going to get any. Right? So essentially what's happening is kind of the last j, the biggest j where you see people and then you stop seeing them afterward, is roughly log t. So then 2 to that j is roughly t. Okay. Does that make sense? Okay, so good. So for fixed j, let zj equal number of I in stream with LSB of h of I equal to j, and let z bigger than j equal number of I in stream with LSB h of I bigger than j. Right, so what do we know? Basically what I said just now in words, I won't write the proof down, is that the expectation of zj is equal to t over 2 to the j plus 1. This is by linear rate of expectation. Right? Each one has probability 1 over 2 to the j plus 1, and then you sum up over all t of them. And the expectation of z greater than j is equal to t times 1 over 2 to the j plus 2 plus 1 over 2 to the j plus 3 plus dot dot dot, which is at most t over 2 to the j plus 1. Okay. Now, this is an expectation calculation. I'm also going to do a variance calculation. Okay, so this is something subtle. When I wrote it, I didn't make you pay close attention, but this actually is important. Now, the second bullet. If you have a bunch of independent random variables, pairwise independent random variables, then variances add. That doesn't actually require full independence. It just requires pairwise independence, like two-wise independence. So we're going to make use of the fact that h is a two-wise independent function. And let me write things explicitly so that you see where this is coming from. So let yi, so let's fix j. Let yi be 1 if h of I, if the least significant bit of h of I is equal to j and 0 otherwise. Right? Then zj is just the sum over I in the stream of yi. Right? Which implies that the variance of zj is the variance of yi, which is equal to, or the sum of the yi, which is equal to the expectation of the sum of the yi squared minus the expectation of the sum of yi squared. Right? And then if you expand this thing out, is equal to the sum over all ij of expectation of yj. Right? So this is why you really only need, in a variance calculation, when sums are involved, you really only need pairwise independence. Because what you'd like to say is you'd like to say that this is equal to the expectation of yi times the expectation of yj. Right? That's what you'd like to say. And that's true if the variables are pairwise independent. Right? I'm only focusing on two random variables at a time. So by two-wise independence, these two guys act independently of each other. Okay? Yeah? Oh, sorry, say it again?
The yi is some function of h applied to the I input, right?
To the integer I in the stream.
So if the same integer comes up twice,
Yeah.
like once at I1 and once at I2, with I1 equal I2, why I1 equal yi2 always?
Maybe, I don't know if this answers your question, but zj I'm saying is the sum of I is like the distinct i's in the stream. I'm summing over the distinct i's in the stream. There are t things in this sum. This is the sum of t things, yeah. Yeah, sorry if that was confusing. Okay, so, right, so you really only need pairwise independence, which we have. And I'm not going to do the calculation for you because I want to get to things. But if you were to do this calculation, if you were to use the fact that the variance of the sum is the sum of the variances, you would get that this thing is at most t over 2 to the j plus 1. Basically, the variance is at most the expectation. You'd get something like that. Okay, so I'll leave proving this to you. Right, so for j star, which is something like log of t, let's say plus 5 or something, right? Kind of at the level log t might not be an integer, but let's say it were. At the level log t, we expect zj to be about 1, right? At the level log t plus 5, we expect zj to be something like 32, right? So what's the probability that zj is 0? What's the probability that zj, so this implies that expectation of zj star is somewhere between, I guess, 16 and 32, something like that. So let's say it's at least 16. Right? So what's the probability that it's 0? That means it had to deviate from its expectation by at least 16. Right? But Chebyshev tells you that that's unlikely to happen. Implies that the probability that zj star is 0 is at most the probability that zj star deviated from its expectation by at least 16, and this is at most, I don't know, sort of like, let's say at most a 10th or something, or a 5th. It's something. You use Chebyshev, okay? We have a bound on the variance, right? We know the expectation. Use Chebyshev, and you get that the chance of that happening is a small constant, right? And then similarly, for j minus, which is like log t minus 5, right? How many people do we expect there? How many people do we expect to have a least significant bit? The expectation of z greater than j minus. How many people do we expect to have a least significant bit bigger than j minus? Something like 1 over 16. Right? But by Markov, so then what's the probability that we see 1 at all? That means we have to be a factor of 16 bigger than our expectation. But by Markov, that happens with probability at most 16, 1 over 16, right? So this thing is like at most 1 over 16, which implies the probability that z bigger than j minus is bigger than 1, that we see anyone at all, is at most 1 over 16 or something. This is Markov. So by a union bound, this means that the last, the last j where we have anyone with the least significant bit of j is roughly log t. It's within a band of a window of size 10 or something around log t, which means we'll have like a 2 to the 5. We'll have like a 2 to the 5 approximation, like a 32 approximation or something. Not that great, but it's a constant factor approximation with constant probability. And if you want to boost that to high probability, what do? Yeah, you could plus it. Actually, here you can go straight to the plussing, right? You can just do a median without an averaging, right? So, because what's going on here? So if you think about what the plussing does, right, the averaging of unbiased estimators, what that gives you is it gives you a good algorithm that gives you like a good approximation with constant probability. Right. This already is giving me a constant approximation with 2/3 probability or something. So I can go straight to taking a median of a bunch of them. Okay. So this is a constant approximation. So overall, let's say, 32 approximation with 2/3 probability. And when I write these numbers, 2/3, 5, etc., I'm just kind of praying that it gives me 2/3. Okay, so if it doesn't, you can just increase this number by another constant or something, right? These constants are not magic. They're just pick them big enough so that you get the right failure probabilities. So, okay, good. So first, we got an O of 1 approximation. How do we refine to 1 plus epsilon? So the moral of the story is that sometimes when you make the idealized algorithm non-idealized, things get a little hairy. But okay, that's okay. So first, let me define algorithm TS, which stands for, let's say, a trivial solution. Okay. Maintains, stores the first C over epsilon squared distinct elements. Okay? It just remembers the stream. It remembers the first C over epsilon squared things in the stream. And then after that, it just stops remembering. It just remembers the first. And then when you ask it how many distinct elements are there, it just tells you how many things it's stored. So observation, this TS algorithm always gives the right answer as long as the answer is small. If the answer is less than C over epsilon squared, it will give you the right answer. If the answer is bigger than C over epsilon squared, then it'll give you a severe underestimate. Okay? So it's always right if t is at most C over epsilon squared. Otherwise, it gives you some underestimate. Now what we're going to do is instantiate TS1, TS, or let's say TS0 up to TS log base 2 of n. So we're going to instantiate roughly log n different copies of this TS algorithm. What we're going to do is we're going to pick a hash function g mapping n to n from a pairwise family. And then, so this is now my algorithm. Feed I, we feed a stream element I to TS least significant bit of G of I. And then for output 2 to the j plus 1 times the output of TSJ, where t is roughly 2 to the j. Okay? So I'm assuming that I know t up to a constant factor. I know a j such that t is roughly, such that t over 2 to the j is such that t over 2 to the j is roughly 1 over epsilon squared. That's what I meant to say. So I'm assuming that I know a j such that t over 2 to the j is roughly 1 over epsilon squared, up to a constant. How do I actually know such a j? Right? That's what that was. So in parallel with this algorithm, I'll run that algorithm in parallel. And then at the end, right, I only need one pass over my data stream because these things are running simultaneously. At the end, when I need to actually output an answer, I'll get my constant factor approximation here. That tells me a j such that t over 2 to the j is roughly 1 over epsilon squared. And then I'll scale back up by 2 to the j plus 1. Or let's say 2 to the j plus 1. T over 2 j plus 1 is roughly 1 over epsilon squared. OK, so that's the final algorithm. I don't want to get too formal with analyzing this. Let me tell you roughly why this works. Oh, and by the way, there might not be such a j, right? What if t is actually 5? Then t over anything is not going to be 1 over epsilon squared, right? T over 2 to the j is only getting smaller and smaller. So in parallel, what you can also do is maintain another TS data structure that just remembers the first 10 over epsilon squared things in the stream. And if the answer is less than 10 over epsilon squared, you know it exactly because of that thing. If the answer is bigger than 10 over epsilon squared, then there is such a j. You'll figure out such a j from that step, and then you'll use that j. OK. So why does this work? Basically, let bj equal number of distinct elements mapped or hashed by g to the jth data structure. The expectation of bj is equal to t over 2 to the j plus 1. This is just linearity of expectation, right? If you have a bunch of indicator random variables that each indicator random variable tells you whether or not item I mapped there, he has expectation 1 over 2 to the j plus 1. So the expectation of their sum is the expectation of bj, which is t over 2 to the j plus 1. Okay. And let me call this qj. Chebyshev says that bj is actually going to equal qj plus or minus O of the square root of qj with good probability. With probability 2/3 or 9/10 or something, some good big constant probability, right? So Chebyshev basically tells you that with constant probability, a random variable is within a standard deviation. That's what Chebyshev tells you. But if this number is roughly 1 over epsilon squared, if this number is bigger than or equal to 1 over epsilon squared, right? Then this is equal to 1 plus or minus O of epsilon qj if qj is roughly 1 over epsilon squared. That's why I zoomed in on the level where t over 2 to the j plus 1 was roughly 1 over epsilon squared. In fact, this is going to be this as long as qj is at least 1 over epsilon squared. Okay? As long as you pick a level that's bigger than or equal to, where the expectation is bigger than or equal to 1 over epsilon squared, you will get a 1 plus epsilon approximation by Chebyshev. So good. So in fact, you get better and better error if j is smaller. If qj is bigger than 100 over epsilon squared, you'll get a 1 plus epsilon over 100 approximation, or 1 plus epsilon over 10 approximation, or something like that. So why didn't I pick j? Why did I pick a smaller j? Why didn't I just pick j to be 0 or j to be 1 or some such thing? So here's what I'm saying in words, okay? So what I'm saying is if you go to a level where the expectation is like 1, if you expect one person, right? If you go to level log t, you expect only one person to be there. But then there's terrible variance. There's a pretty decent chance that no one's going to be there. There's a pretty decent chance that 3 people are going to be there if the expectation is 1, right? So you're not going to get a 1 plus epsilon approximation with good probability because there's just too much deviation. But if you expect 1 over epsilon squared people to be there, Chebyshev tells you actually you'll have very close to 1 over epsilon squared with good probability. You'll have 1 over epsilon squared plus or minus 1 over epsilon, which means you're getting a 1 plus epsilon approximation, right? So the bigger the expectation is, the better quality multiplicative approximation you're getting. So I said, let's go to the level where the expectation is 1 over epsilon squared. Why didn't I say, let's go to the level where the expectation is 1 over epsilon to the 10th? We'll get even better multiplicative error. Yeah. Yeah, exactly. The problem is the TS algorithm stops working if the number of distinct elements in the stream is too big. Right? So yeah, you could go to the level where the expectation is 1 over epsilon to the 10th. But the TS at that level only remembers the first 1 over epsilon squared people. Right? So you're not going to get a good, you're not going to actually know how many people landed there. So if you go to the level where the expectation is roughly 1 over epsilon squared, you actually will have roughly 1 over epsilon squared with good probability. So you both get a multiplicative approximation, and the TS at that level will work. Right? And then you scale back up by 2 to the j plus 1, and then you get t. So minus calculations, that's what's going on. That's why this algorithm works. And the final space, well, we need to remember, we need to run that algorithm in parallel. That's log n bits. We need another hash function g. That's another log n bits. And then for each of there are log n different levels in this, log n different streams that we're running in parallel, right? TS0 up to TS log n. For each one of them, we're running the TS algorithm. How much space does the TS algorithm use? Yeah, exactly. It remembers C over epsilon squared numbers. Each one is log n bits. So this uses C over epsilon squared log n bits, and there are log n of them running in parallel. So the total space is 1 over epsilon squared times log squared n. And there's no idealized assumption here, right? This is just the truth. And it turns out it's possible to get an algorithm using space 1 over epsilon squared plus log n bits. This is a paper by Daniel Kane, myself, and David Woodruff. And this is actually optimal. You can prove that, or it was proven by Woodruff and others, that there is no algorithm that uses less space than this. Okay? I'm not going to cover this algorithm in class. But it uses similar ideas where you have parallel streams and do stuff. Okay? But I'm not going to talk about the details. But anyway, now you know an algorithm that runs in a non-idealized algorithm that actually runs in very little space. Okay? So I didn't get to the impossibility results. I'll do that at the beginning of Thursday. So that's everything. And please sign up for scribing. Okay? We have very few scribe signups. You scribed today, right? Okay, great. Okay, good.